Okay, so what we are going to do is continue our foray into max flow min cut and max flow min cut. Today we'll see some algorithm as well as we'll see the proof that max flow is equal to min cut. So that's the goal of today, and let's see how much goal we are able to reach today. So the setup which we were working on. So what was the setup? Our setup was that we have been given input was given a directed graph, okay, some say v comma e, and then we had a capacity function on didn't we have some capacity? Yeah. So we also had a capacity function e to r greater than equal to 0. So okay, and we had to output what we call flow. So flow is basically a function from e to r positive with certain constraints. What was the first constraint? We call feasibility constraint. So feasibility constraint said for all e, f of e lies between is at least and capacity of e. And secondly was conservation. Okay, what was conservation? Conservation was that for all v, right? For all v, what is coming in is what is going out. So we defined the notion of net flow. Okay. So what did we define? Notion of net flow. So what is notion of net flow? Is v is basically what is going to come in minus what is going to come out minus what is going to get in. So that is basically for all u, flow from v to u minus all w, flow from w to v, right? Right? And what was that? So this was the net. So for all v, delta of fv equal to 0 uh, except for s and t. Okay, so if there is s and t given to us. Okay, and what was the flow value? The flow value was nothing but, so we assume that s is source, t is sink. Okay, t is sink. What was the flow value? It was basically partial f s. So something is which is same as partial f t. No, it is same. Sorry, negative. Okay. So this was the setup we were working on, and we defined the notion of cut. Okay. So what is an ST cut? So ST cut was basically partition of my vertex set V into S disjoint union T. Okay. So partition is S union T. S is contained inside here, T contains inside here, and we defined the cut value ST is equal to summation the capacity of all the edges that is with one endpoint in S and other endpoint in T. So summation over V in S, W in T, capacity of VW. Okay, so this is what we defined the capacity. Okay, and so what is a min cut? Min cut is a partition into ST that minimizes the quantity S comma T, right? And what is the max flow? Okay, max flow is finding F that maximizes this function. And we said that, oh, max flow is equal to min cut. Okay, so we'll prove this. But before, so this is the setup we have been working on. Okay, I'm going to make one. I don't think it's necessary, but okay. So let's keep one example in which might be illustrative. Okay, so let's take one example of a network. Okay, so this is S, this is T, okay, and S and T. This goes here, comes here. Okay, so this is a network, a directed graph, and so 20. So whatever the second thing, this is capacity, and this is flow. Okay, this is 10 on 10. This is 0 on 10. This is 0 on 15. This is 0 on 5. This is 5 on 15. This is 5 on 10. And this is 10 on 10. This is 5 on 20. Okay. So notice, so this is a feasible flow. Why it is a feasible flow? Because look at any edge, right? Whatever value I have assigned by function is less than its capacity and it is non-zero. That's the first thing. So this happens, and except this, look at this. How many unit of flow is going in? 10 unit of flow is going in, and how many unit of flow is coming out? 10 unit of flow is going to out. So this is perfectly fine. And you just check for any other constraint, and this will be satisfied. So the first lemma or the theorem which I'm going to prove to you today is the following lemma. Okay. So for example, in this, so if I would have taken as this F, as this T, then what is the capacity of this cut? This is a cut because this set S contains S, this set T contains T, they are pairwise disjoint and their union is whole vertex set. What is this definition tells us? It is the capacity of the edges which are leaving S and going into T, right? So which is 5 and 10. So capacity is 15, right? So for this particular cut, a different cut could have a different capacity. For example, if I would have taken this and then I would have got something very different. So this is all that it is. Okay. Okay. So what I'm going to prove to you, so this is a lemma which I'm going to prove. Okay. So this is a setup we are going to work, and I want to prove that max flow is equal to min cut. But before we even make an attempt to prove this, I'm going to prove a lemma which will be useful in our setting. So here's my lemma. This lemma is nothing but just a sequence of some inequalities, but still, I mean, we have to do it. So what does it say? Let F be any feasible flow. Let F be any feasible flow. Okay? It means it satisfies these constraints. Okay? And feasible, let's not call it any flow, but ST flow. Okay? And any ST. And let S comma T be any ST cut. Okay? Any ST cut. Okay? The value of F is at most, this is what it says. The value of F, look at the flow, value is at most this. That's the first thing. Okay. And what is the second thing? Moreover, if this holds with equality, then something nice happens. If and only if F saturates, okay, F saturates every edge from S to T and avoids all edges, avoids every edge from T to S. What is the meaning of this? The last line, if you look at any edge, the flow is same as the capacity, and look at any edge which is going inside, the flow on those is 0. That is what means avoids, and it's equal to the saturated. Okay. So how do we go about proving this? Okay. So let's go about proving it. Okay. But notice what it tells us. You started with any feasible ST flow, and you start with any ST cut, then the flow value is upper bounded by the cut value, right? So for any feasible flow and any cut, this is true. And it makes complete sense because, like, I mean, you have to pass from S to T. I mean, that's all that you can use. But now let's make it formally prove it. Okay. So what is the F? Is basically by definition, this is delta of F of S. Okay. Now, which is equal to summation. I just add some zero quantity. What do you mean by add some zero quantity? So I look at summation V in S delta F of V, right? Why? Because except S, if you notice here, net flow, this is equal to 0 except for S and T. So what I'm adding only 0, 0, 0, 0, 0. So from here to here, it's fine. Basically adding 0. This is what we are doing, right? We have added some zeros. Now let's expand it. Let's expand the definition of this. So by definition, what is this? V in S, okay? What is this delta FV? It's basically what is going inside V, what is going outside of V and what is coming inside. So let's write it down. U, okay, it goes over all U, flow from V to U, right, minus summation, and look, I am running over all possible U's. Doesn't matter because anyway, look at V and look at U's. All those vertices which does not have edge, they are anyway 0. So I can basically sum over all U's, right? And what is this? Minus summation going over all W, right? F W to V, right? Am I right? This is what it is. Now, which basically I can, since I can go through this over all U's, over all W's, I can write it down basically summation V in S, summation U F V W minus summation V in S summation W F W to V, right? I can write it down. I just like taken this in and this here. So V to U, right? W to U or V. Now this is correct, right? W to V. Agreed? So this is just the inequality. Now let's look at S. Look at S and look at any edge here, XY. Right? So for X, you are adding it as, for this edge, what are you adding? The flow value remains the same. So for X, you are going to add what? Flow, for X, you are going to add flow X to Y as a plus quantity. But for Y, what are you going to add? Minus flow of x to y, right? So for every edge which is inside, this cancels out, right? Once it appears positively, others it appears negatively, so they will cancel out and they will become 0, right? So now using this idea, I can write down the next step only over, I can write down here u not in S and w not in S, right? So I can write down this summation, okay, v in S. So because others are not contributing anyway, summation u not in S. So this is outside, okay, f v u minus summation v in S summation w not in S, right? F w u to v, right? So basically now if you look at a picture wise, what is now it is counting? This is counting these kind of edges and this is counting these kind of edges, right? Now what do you know about flow value? What do you know about flow? Because flow is at least 0, this quantity is some non-negative number, right? So I can write down this is less than equal to summation v in S summation u not in S f vw vu, right? Right? Because this is a non-zero quantity. But what is this quantity? This is also upper bounded by the capacity. So this is summation v in S summation u not in S capacity of v2 u. But what is this? This is exactly equal to the definition of cut, right? This is by definition, okay? So we used inequality twice, okay? Okay. So in this, this proves the first part, right? So whatever our intuition was, we have made it formal proof. Now here is inequality 1 and here is inequality 2. When can this be holds with equality? When will this hold with equality? This holds with equality if and only if when, right? When all this quantity has 0 value, right? If and only when, because every quantity is positive, if and this holds with equality if and only if when say what this called capital X, when X is 0, which means flow on them is 0, which means flow avoids edges from T to S. Excellent. Now when will this hold with equality? This holds with equality when this flow is equal to capacity, which means this holds if and only if, because all these are again positive quantity, if and only if when F saturates all the edges from S to T. That's it. So we have proved this. All well? Do you have a question? Okay. So this is a lemma which will be useful for our purposes. Okay. Now, so let me leave it for now. Let me run the model. So what is our goal to prove? So this is the theorem we want to prove, okay? What does it says? It says in every network, uh, with source S and sink T, okay, with source S and sink T, target T, the value of max flow, right, the value of max ST flow, not any flow, max ST flow is equal to, okay, is equal to the capacity of minimum ST cut, okay, ST cut. So this is a theorem which I want to prove. And towards this, we started to define. So I'm going to, generally we first prove and then algorithm comes. First I'm going to give you some sort of algorithm and that will lead us to the proof. So we define the notion of residual network. So what is a meaning of this? So suppose residual network, means, okay, I'm flowing this much, how much more can I flow? Ideally, the definition should have been like, for example, here in this, okay, I'm 10 units is flowing. So if I write down here S, okay, maybe there are some more edges, okay, you will tell me. Okay, so how many units are flowing here? Already 10 units are flowing. How much is left? 10. So it looks like, oh, there is a chance that we could send 10 more units of flow here, right? This is what, like this much is remaining, like the capacity of this channel is 20. I have utilized 10 and 10 is left to be used. So this is 10. Here I have utilized 0. So 10 is still to be used. How much do I need to use? How much have I used here? I have used 10 here out of. So I cannot use this anymore. So just forget it. I mean, if I cannot even use it, then forget it for now. Like this is what most naturally people should be doing. This is 0 to 5, right? I'm using nothing. So I have 5 units of flow. And then let's look at this. How much it is allowed? 15 unit of flow. How much I'm allowing myself? 15 unit of flow. 0 flowing, 15. But how much am I using here? Huh? 10 out of 10. So I cannot, I don't need to. I mean, like this channel is completely full. Now, look at this. Okay, look at this. So how much it will be? 5 unit of flow is there and 5 is left. Here 10 is left and here 15 is left. So suppose, I mean, this should be the most natural way of defining residual network. That, hey, look at the channels, I'm using this much and I'm not using this much. So that is what is remaining. And we should try to find a path from S to T. We should try to find a path from S to T in this network and try to augment the flow along. For example, just find a path from S to T here. Is there a path from S to T in this network? Yes, like there is a path. I can go along this path, and this path. This is a unique path. I cannot go anywhere else. So now, fine. So it means that I should be able to augment S to T along this path, right? And since I'm only writing capacities here, which is remaining, I will add minimum of this because I cannot add 10 everywhere, right? I can only add minimum of 5. So let's try to add that minimum of 5. So now I make it, so this tells me that along this path, let's give more flow. So I Now how much it becomes? 5 I floored, so 15. This becomes 5 on 5, and this is also will become 10. Done. Okay. But now if I write down the residual network of this, what will happen? Now of this particular graph, the way I define my residual network, let's see what happens. How much is left? 5. Is there a path here? This doesn't exist anymore. This becomes 5, right? And I did not use anything anyway, so this remains the same. Now I cannot find path from S to T. But does that mean that, so what is the flow now? 15. But this is stupid, no? Why? Because look, let me increase the flow value, okay? Look at this path. Oh, no, this is used. Okay, so this is used. Okay, so in some sense, it looks like if this is how I define my residual network, I mean, things could happen. So let me give another example. Maybe this is optimal, this may not be optimal, but let me give another example. Okay. Look, if I can find a augmenting flow like this is great for us because all I am doing is I am increasing everything. So nothing to prove anyway. But let's assume just 4 network graph. This will be a useful example to have anyway. Everyone has 1, 1. So this is my capacity. And suppose my flow is this. This is my current flow. And I defined my residual network the way I defined. So let's do this, 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 this. Okay? Suppose it. So now what will happen? What will I get? This is full, nothing I'm going to get. This is full, nothing I'm going to get. This is underutilized, so I'll get 1 here. Okay, this is fully used. Am I going to get anything? No. What I'm going to get? 1 here. Is there a path from S to T in this? Okay. But clearly, this is not a max flow for sure because I could have not used this edge, used 1 here and 1 here. So flow is 2, but this only gives us, right? So this natural way of defining network is residual network is not the right way, right? So what we define, we say, hey, why should, maybe the right way of approach is I push some flow out and then distribute differently, right? So that may be the right way of doing this. And this is why we define residual network is that if I'm flowing in this direction, then I could come back. So come back means I put back an arc here which allows me to come back by certain quantity, right? So if I can use those paths in those edges, I will go and decrement the flow, right? And you will see, so this is why in residual network we allow ourselves also that maybe the best thing is to not use this arc, right? And reroute things differently, right? So I have to give this option to the flow network, right? And hence this natural way of defining residual network is not the right way about it. Okay, so I just wanted to give you, and just remember this example. It's a, I mean, for a long time I did struggle that this is how it should be defined, and but once you see an example and you understand, then you know why it is defined the way it is defined. Okay, because for me, like, okay, fine. I mean, allow more. I mean, then it's like a greedy. See what happens, because you started with some arbitrary flow, right? Maybe you made a bad choice in the beginning itself, and now you want to make it push to get it why? Okay. So how did we define residual network? So for now, first I want to make some basic simple assumption, is that the input graph G has a property that between any pair UV there is at most one arc. It is not very hard to enforce it. Why? Because suppose you had some U and some V, and you had say some 10 and some 17 flowing in, I can just transform it, U, add one single node, V and single node, and make 10 here, 10 here, 17 here and 17 here, and get this assumption. So this is not something which I am assuming, but it will make our what do you call our analysis slightly cleaner to present. So I'm going to make this assumption that between any pair UV there's at most one arc. Otherwise we could have done this. So this is not important to understand the concepts. Okay. So how do we define the residual network? Okay. Right. So first let's define the notion of residual capacity. Okay. So first let's define the notion of residual capacity. So let F be any flow, any feasible flow. Okay, F is any feasible flow. Okay, so by feasible flow we always mean that it is between 0 and capacity, right? We don't try to prove that it satisfies conservation and this, nothing. It will automatically satisfy these things. Okay. Okay. So we define a new capacity function from V cross V to R positive. Notice that capacity function was from edges to R positive, right? And you can assume that capacity for other edges is equal to 0 for all that you care. It doesn't matter. But for capacity, I need to define from V cross V to R positive, because I might, in residual network, I might have edges which are not present in the original graph. Important point. So how should I define this? So how do I define C of U tilde V, like some edge, is the following thing. So either this UV is present in my graph or this UV is not present in my graph. So suppose U comma V is present in my original graph. Then, hey, I'm allowing you to flow this much. Already this much is flowing. How much more can you flow inside this direction? So it is like capacity of U comma V minus flow of U comma V. Right? U comma V is not in E, or rather say V comma U is in edge. Then what is this? Flow of U comma V. Because that is all you're flowing, that is all you can push back, and 0 otherwise. Okay? So this is what is called residual capacity. So this is what is called residual capacity. Notice, because F is greater than or equal to 0 and C is greater than or equal to 0 everywhere, residual capacities are also non-zero. Okay? Residual capacities are also non-zero. Okay? Okay, let's go back to my previous flow diagram. What it was? Do you remember? It was 10 out of 20, 0 out of 5. Right? And it was 5 out of 15. Right? Okay. So what is a residual graph? What is a residual graph? So I define residual graph GF, vertex set remains the same, and EF. What is this? Those pair in V cross V for which residual capacity is positive. Capacity is positive. Let's try to construct a residual network of this. So what will the residual network of So what will be the residual network of this? And look, in residual network, I will not be able to assume that between any pair UV, this like by nature it will have lots of pairwise edges. So suppose if I try to write down the residual network of this, what it will be? ST. Okay. So how much is flowing in this direction? In this direction, 10. So what is this residual capacity here? Is 10. And what is the residual capacity of this guy? 10. So for every edge which is present, for any edge which is present, either both are present or at least one of them is present in any residual network, right? So when is both present? When you are utilizing this partially, right? When you are utilizing it completely or is completely saturated, then all you will get is the other arc, okay? So here it is 0 to 5, so this is 5. So will you get this other arc here? No, because it is 0, right? Similarly here 10 to 10, so you are only going to get arc in this direction, which is like 10, right? Now nothing is utilized here, so how much it will be? 15. Okay, has anything been utilized here? Nothing, so 10, right? And has anything been used here? Yes, all the 10 unit has been flowed. So this will give us 10 and other direction has nothing, 0. And similarly here if you notice, how much has been used? 5. So this is 15 and the other direction is 5. Similarly here is 5, so 10 and the other direction is 5. So this is how you construct a residual network, okay? Okay, so now we have two cases to consider, okay? We have two cases to consider. Either G of f has S to T path or not, okay? This is what it is. So GF, which one? Oh yes, sorry. So this will be 10 and no 5, sorry, and this will be 5, sorry, thank you, okay. So first let's assume that it contains a path, okay. So we can have two cases, either there is a path from S to T or it does not contain a path from T. So let's see what happens if it contains a path from S to T. So let's consider that case. First, so you understood what is G of f graph is. So, and what residual capacities are. Okay, maybe I think this is better to read this. Okay, and so for example, what is the path here? Is there a path in this network? So give me one path from S to T. So one path is, this is one path possible. No? Is there any other path possible? I could have also gone this way. Look, I cannot come here. Yeah, so there are like lots of paths. Okay, so for example, this is right. I could have come down along this path, that's better, and then gone like this. Okay, then gone like this. Okay, so first let's assume that GF has a path P from S to T. So this is what we are going to assume. Okay, and these are called augmenting paths. This is precisely what is called augmenting paths, because we can augment flows along this path. So as we saw, look, if I want to assign every like flow, I can only assign the bottleneck. And what is the bottleneck? The minimum amount I can push without violating the capacity constraint. Okay, which means, so I have to define some number f. So what is f? Let's define f as minimum over. So I go over every edge. Okay, right? Minimum over u comma v in P, and what is it? That's it. So this is what my flow is. So this is what means that this is the maximum amount I can send across this path without violating the flow constraint. Okay. Now notice first of all, f is non-negative. F is greater than or equal to 0. Why? Because only edges we had in residual network had non-zero residual capacity. Okay, good. So this is what is. So now I'm going to define a new function from E to R positive. New function, right? I have to define a new flow function. So what is this new flow function? I say, well, look at f prime u comma v. I have three cases. Either this edge belongs to the path. So look, uv is in E. Now if uv belongs to the path, then what you should do, I am moving across and I am the edge inside this. So what does it mean? Oh, I can send some more flow on this path. So this will be f of u to v plus f. Now what happens if v to u is in path? It means actually in original graph u to v is an edge. So on this I should decrease the flow, right? So what it will be? F u to v minus f and f u to v otherwise, right? So this is how my new flow function is. So now if I try to do this with respect to our flow function, what will we get in this example? So okay, so still we are sending 10 unit of flow before also, and we are sending 10 units of flow now also. But along this, how much unit of flow I am sending? 5 units. Because what is the minimum of 10, 10, 5, 5, 15 is 5, right? So how much unit of flow now I will be sending here? 5 unit of flow. Excellent. So I am sending 5 unit of flow from here. Now I was sending a 10 unit of flow here, but what does it tell us? That please you only send 5 unit of flow here. So I send 5 unit of flow here. Fine. Now, what does it tells us? Oh, along this path, please send 5 unit of flows. Okay, so sends 5 units of flow. Okay. Now, what does it tells us? Along this, I am taking a black edge. It means, what does it mean? I should decrease the flow here to 0, right? I was sending 5 unit of flow, decrease it. So now this becomes 0. Okay, that's that's not right. And along this, I have to send how many unit of flow? 5 more unit of flow. So I will send 10 unit of flow. Now before I was sending how much unit of flow? If you notice, 10 unit of flow, but now I am sending 15 unit of flow. Now, do you know why always flow will increase using this? So look at the flow. Look at this path. On this path, there is only one edge coming out of S, and that is a real edge in my graph, because S is a source. S is a source. So either the edge goes back, then I cannot use that from the path. So you are sending a real, and for every other edge, flow is not changing. So from the one real edge, you have increased the flow by whatever the F quantity. So the new flow will be F plus F. Right? So that is an idea why flow always increase, because there is a unique edge from coming out of S, which is a real edge, and that on that edge I have increased the flow, and all other edges which were part of the previous flow, they remain the same. So flow quantity can only increase. Okay, so this is an example, an illustrative example. Now let's see. Now you know why will I don't have to prove conservation? Because why do I don't have to prove conservation? I never have to prove conservation for F prime. It automatically is, because you are adding, subtracting the same quantity everywhere. Okay, so only thing which is important to show is that why this is a feasible flow. Okay, so let's show this is a feasible flow. It's not very hard to show, just let's show that this is a feasible flow. Okay, need to show F prime is feasible. That is, for every edge u comma v, right? What I have to show? F prime of u comma v is less than or equal to capacity of u comma v, and which is greater than or equal to 0. Okay, so we have 3 cases to consider. Okay, first, if P contains the edge uv. If P contains the edge uv, then what happens? Then notice, by definition, F prime of u comma v is F prime uv plus F. Do you agree? By definition. And since F is a non-zero quantity, this is at least greater than or equal to F uv, which is greater than or equal to 0. Right? Because F was a feasible flow. So that was greater than or equal to 0, so that implies this. Now how do I show that it is upper bounded by the capacity? Okay. Okay, now notice, what is F prime of u comma v? Is F of u comma v plus F, right? This is what we know about. Okay, and what is this? This is less than or equal to F of u comma v, and what is this? uv is on the edge, so it is less than the residual capacity because F was minimum over all edges. So this is less than or equal to, right? But what is the definition of residual capacity of uv? Well, the definition of residual capacity of edge UV, if UV is present on this edge, it's CUV minus FUV, right? So this is equal to, by definition, FUV plus FU plus CUV minus, I should stick to same notation, right? Minus FUV, this gets cancelled, this is capacity U10, right? So this is done if UV is part of this, okay? Let's see the other case. If the augmenting path contains, I would like to keep this, I would like to keep this, I would like to keep this. This is simple, so I'm going to drop this, okay? This is like our workspace, okay? Because then it is easy to verify, okay? So if the augmenting path P contains the reverse edge, okay? Contains the reverse edge V comma U, okay? What does it contains? Reverse edge V comma U. So now let's see what happens. What is the definition of F prime UV? So then the definition of F prime UV, if it contains the reverse, is this minus F. So which is F UV, yeah, right, minus F, right? Minus F. What is this? This is definitely less than equal to F U prime V, because this is a positive quantity, and which is, because it is feasible, it is less than capacity of U tilde U comma V, right? So now we need to show that this is equal to 0. So let's try again. F prime UV is F minus F. Now minus F, okay. So what is the definition of, so what is this? This is, I can write it down, now it's a lower bound, I can write it down FUV minus capacity of V comma U, no, U comma V. Or V comma U, I think it should be V comma U, no? Yeah, it should be V comma U, because VU appears on the path. Look, I have an edge UV, but it appears as VU on the path, and this is this. So this is what I can say, okay? But what is the definition of VU? It is nothing but, if VU is an S, then it is FUV, right? So for us, UV is an edge, so it is F, yeah, so FUV, right? So this is equal to FUV minus FUV, which is equal to 0. So we are done, okay, good. And what happens if the edge does not appears, its flow value has not changed, right? For UV not on P, right, f of U comma V, sorry, f prime of U comma V is f of U comma V, which is less than equal to 0, less than equal to capacity of U, done, right? So what have we shown? So whatever flow function I have defined to you is this. So what does it shows to us? That if a residual network does contain a path, right, or like does contain a path from S to T, then we can increase the flow, okay? Then we can increase the flow. So now let's look at the case when there is no path, okay? Okay, now we don't need all this. Okay. So what we show, okay, conclusion from here. If GF contains S2T path, we can augment. Okay, if contains this path, we can augment. Okay, suppose that GF does not contain a directed path. Suppose GF does not contain a directed path from S to T. Let S be those words V reachable from S in GF, right? And since T is not, since no S to T path, what does it implies? T is not in S, because otherwise you would have this. So now let's take this S, this T. Okay? Clearly this is an ST cut because it contains S, it contains T. Right? T is basically V minus S. Okay? So what do we know about, for every vertex U in S and V in T, what do we know about this? What do we know about this? For every vertex U in S, V in T, what is this? What do we know about this? So capacity of U comma V is equal to what? So look, either there is no edge, then there is zero, who cares about it? Otherwise, what is this? Capacity of U to V minus flow from U to V, right? I want to say this is equal to 0 for every pair UV. Right? Because look, if there is no edge, nothing, but suppose you had an edge here, right? That edge is no more present here. So this happens. It means there is an edge with flow U comma V from V to U. There is a V to U with flow U comma V. It shouldn't be V comma U, it should be flow U comma V. Is it okay? Look, I am talking about how do we define flow? It is V to U, no? This is equal to 0. Agreed? Because we added this edge in residual graph V to U with flow V to U.
But that, if we add in the residual graph, then flow should be from U to V. In that capacity function residual graph, if you have an edge from V to U, then the flow would be U to V.
So if there is an edge from U to V,
Then it's fine, but now we have an edge from V to U.
no. What I am saying, U is here, V is here. Okay? Now for any U and any V, I want to write what is the residual capacity of UV. What is the residual capacity of UV? It depends, backward arc, right? So suppose there is a forward arc. right? Then this is true, right? Okay. But what is, I also have in residual graph arc from V to U and
Edge in the actual graph. We use the edge in the
actual graph.
The residual graph will have this FV to U value as a residual value.
True. Okay, so this is the actual edge. Okay, pick UV, and okay, so pick UV, any pair of UV. So now look at UV. Okay, I could have a graph like I could have an edge of this nature. Then this part is true. Okay, now what else is this? Now suppose there is an actual edge from V to U. Look, okay, there is an actual edge, right? Then what is its flow value? It's just flow value is F from V to U, right? Now the point is that, and why this is equal to 0? There is no ST path, okay? Because no ST path. Okay, what is the meaning of this? This is a positive quantity. This is a positive quantity, like non-negative quantity. It means individually this should be equal to 0 and individually this should be equal to 0. What is the meaning of this? Right? So it means individually is greater than equal to 0, or right? We know this, and we also know this f v to u is greater than equal to 0. But their sum is greater than equal to 0. It implies capacity uv minus f u to v is equal to 0, which means f saturates every edge from S to T. Okay? Right? Okay. And avoids every edge from T to S because this quantity is also equal to 0. So what do we know at this point of time? So if there is no path, then mod f is equal to mod s comma t, right? And that shows maximum income. Okay? So now we have proved this theorem. So what we actually showed that you compute this residual network, either you can increase the flow. If you find a path, you can increase the flow. If you can't, then the flow is equal to ST. And that's it. Okay. So we are done. Because look, first part already implies that for any cut mod f is less than equal to ST. This already implies that, like, look at any feasible flow and look at any ST cut, this is true. Now all we needed to show is this greater than equal to this, which this inequality shows. Right? Because if this is not, then I can find a path, augment it and elongate. So now what algorithm does it gives us? What does it start? What algorithm do we get from this? This is what is called Ford-Fulkerson algorithm. Okay? What is an algorithm? This is called Ford-Fulkerson algorithm. What is this? You have a G and start with f equal to 0. Okay? Compute GF, check path from S to T, augment, repeat until GF has no path from S to T. Right? So this is an algorithm. Right? I start with a zero flow, that's a feasible flow, right? And I look at my residual network, I find a path, increase my flow. Now notice that this algorithm could take, how much time does it take? This algorithm will take time order maximum flow value, so let's call that f star, times like m, because you might have to do directed reachability BFS DFS, so like m time. But the value of f star could be huge, right? So for example, let's look at the same network which I drew here, S x some value x, okay, right? V and same guy.
But that bound, you are assuming that we have integer capacity of
Wait. Yes, I'm assuming lots of things. I'll make it clear. Don't worry. Okay. So suppose this is x, and this is 1, and this is t. And yes, I'm assuming that all capacities are integer. Okay, I'm assuming that all capacities are integers. Okay. Now notice that what could happen all the time. I can start from here, and every time how much will I go? I'll say okay, fine, now I find a path here, 1 1, right? Again I will find this one. So you could actually take roughly, right? So you could just alternate between this and this, alternate between this and this, and you could take as many as time. You can show that, like, in, if you have a bad luck, because you're not telling how to find these paths, right? All you're saying, find me any path from S to T. So this could just run order x time, okay, order x time. But now notice that these are integers, but all we are worried about is the size of the input is polynomial. So if x is polynomial many bits, what number can it, if x has poly many bits, what number can it store? It can actually store 2 power x, right? So this algorithm could be exponential, even, could be exponential even for integers. Okay, and I'm not going to the example because I want to do another algorithm. In fact, we can construct networks where this algorithm may not even end, this algorithm may not even terminate. Okay, I'll give you an example, and I will not prove it. Prove it for yourself. This is not important. Okay, so here is one of the simplest example which we are aware of. This is S, this is T, this is some quantity X, this is X, 1, 1, and this is X, this is some quantity X, this is X, okay, and this is phi. Where what is phi? All of you know, right? Where phi is chosen so that 1 minus phi is equal to phi square. So this is basically golden ratio. You can show that this will never terminate. So if you have an irrational number, there are possibilities that this will never even terminate. Okay. So in the remaining 15 to 20 minutes, I'm going to give you an algorithm which is really polynomial. It does not depend on the weights or anything. Okay. So the heuristic which I'm going to apply is called. So now algorithm will remain the same. It's just that what path do I find in residual network? Okay. So I'm going to find a path. Okay. Okay, let's see. Okay. So here it is. Algorithm is exactly the same. Find an augmenting path. But now I'm going to choose the augmenting path of shortest length. That's it. And this I can find using BFS. Right? I'm not talking about weight, nothing. Right? Shortest, what you call length in residual network. So this is my algorithm, end of it. So I do the same thing. While there is a path from S to T in the residual network, just repeat this process. But so what is the running time of this algorithm is order m, which is number of edges, times the loop, times we find a path in residual network. Okay. So if I bound number of times this loop will run by polynomial function, I'm perfectly happy then. Okay? Okay. So let's do this. So algorithm remains the same. It's just that I have changed the heuristic to find okay. So let's define some notion. Let Fi be the flow, okay? Let Fi be the flow or the current flow after ith iteration. After ith iteration. Okay? And Gi be the residual graph computed with respect to Fi. Okay? Now what does this? So for every vertex, I'm going to define a notion of level. So what is Z0? It's G, and what is F0 is 0. Like all flow values are 0. Okay? So for every vertex V, what is a level of V in I? Okay? This is equal to denote the unweighted shortest distance from S to V in Gi. So forget weights. What is the shortest distance from S to Vi? This is what is the level of V. Okay? And if a vertex is unreachable, then I put level of I V equal to infinity. So basically level is nothing but which BFS layer, if I start a BFS from S, which BFS layer it appears. That's it. Because if you do BFS, you will find the shortest path starting from S. So basically it's a layer, this is what I'm calling it, it's a layer number in the BFS tree. Okay, this is basically a layer number in BFS tree starting at S in G. This is what it is. The basic lemma which we are going to prove, okay, so this is the lemma which we will prove and then we will be done. Okay. So let's prove a monotonicity lemma. Okay. What is this? It says that level of I of any vertex V is greater than or equal to level of V in I minus 1 for all V in V and I greater than or equal to 0. Suppose I prove this lemma for you. Suppose that level are monotonic. As you go in residual network, level can only increase, it can never decrease. Suppose I prove this. Okay? Then let's see if we can bound this everything. Okay? So here is the lemma. First let's prove this because that will give us a bound and then we'll come back and prove this lemma. Okay? So first it's like a magical lemma. Okay? So what does this tells us? This is called Edmonds-Karp algorithm. Okay? During the execution of Edmonds-Karp algorithm, each u comma v, each edge uv appears at most each edge uv disappears at most mod v by 2 from the residual graph. Okay. Now suppose we prove this two lemma, are we done? Look. Okay. What does it tells us? Each edge disappears, like during this process, each edge, so suppose I have G0, then G1, G2, dot dot dot, GQ, like, and then it ended. What does it tells us? Okay, now any edge UV disappears certain number of times. So during the execution of EK algorithm, each edge UV disappears at most P by 2 from residual graph. Okay. Okay. So notice, suppose I fix an edge. It disappeared here, disappeared here, disappeared here. But I know the total number of times it disappears is at most n over 2 times. Now I am claiming each time at least one edge disappears. Why? Because someone becomes tight. Right? Each iteration at least one edge, okay? Each iteration at least one edge disappears, right? The one which becomes tight. What does this imply? Right? Every time at least one edge disappears and no edge can disappear more than n by 2 times. So Q is upper bounded by n by 2 times m. right? So the running time of this algorithm is going to be, right, m into n into m, so which is order m square n. Okay, now let's try to prove these two lemmas back by back. Okay, okay, I don't need these things. So this lemma is very simple to prove. The second lemma, monotonicity lemma, requires slightly difficult argument, but suppose u comma v, okay, is in two residual graph, say gi and gj, okay, two residual, say j plus 1, and it is not present but not in any of gi plus 1 to gj. It is here, but not somewhere in between. So what happens in gi plus 1, it vanished. To vanish, so look at the gi and look at this path p. How will it vanish? The only way for him to vanish is like v appears on this path edge, on this shortest, like uv appears, u and v is an edge, right? What is the meaning of this, right? And after that this disappeared, right? So there is no vu arc, so there is only uv arc here. So what is the level number, level of okay, so now, so level of I of v is equal to level of I of u plus 1, because it's a BFS layer, so v will only appear after u, right? So this plus 1. Okay, now let's go back and check on the jth augmenting path. So look, suddenly uv appears, it means vu is on the augmenting path where in gj, only then uv appears. What is the meaning of this then? Level of j in v is equal to level of j of u minus 1. Okay, great. Right? So now let's put together. So level of j in u is this, right? What is this? Is equal to level of j of v plus 1. Okay? Now I is greater than equal to, so because of monotonicity lemma, j is after I, right? So what will it imply? It imply level I v plus 1, right? Now what do I know? Level I of v is level of I u plus 1, right? So this is level I of u plus 2, right? So what we know, every time it reappears, or every time it reappears, what is the meaning? The level increases by 2, but it is the shortest path. So shortest path cannot be more than n. So this is why, right, disappears at most n by 2 from the residual graph. N by 2 from the residual graph. So this lemma we have proved, right? So only thing which is remaining is monotonicity lemma. Let's try to prove this. Okay. Do you people have 5 minutes? I just need 5 minutes to prove this lemma, then I will be done. Okay. See, these are like, once I have explained to you the concept of level, it's like not very hard. But how will someone come up with this concept, that this concept is good enough for our purpose, is not obvious. Okay, but notice this algorithm, now that we prove this, it does not depends on the weight, cost, nothing. It purely depends on the number of edges and number of vertices. That's it. Okay, so now how are we going to prove this? So generally these kind of things are proved using induction. So we will also apply okay, so we fix an arbitrary integer I greater than equal to 0 and v in v. Okay. So we are going to apply induction on level number, but not on index, not on ith round, but on level. Okay. And this is a trick. We will apply induction on level. Okay. On the v and not integer I. So what is our inductive claim? Inductive hypothesis is for all u, okay, for all u such that level of IU is less than equal to level of IV. What I know? Okay, what I know? Who has strictly less? We know that level of what is that called? Level of IU is greater than equal to level of I minus U times U. This is already done. This is what I mean by when I apply on the induction on the level, I fix some vertex V and I'm going to apply induction with respect to this V, the level numbers of this V. I have fixed vertex V and I'm fixed this. So his level will be 2, 3, 4, 5, 6, 7. I'm going to make induction based on that number, whatever that number is. Right? And this is also, if you think like it is increasing 1, 2, 3, 4, 5, 6, and then I'm going to show to this too. Right? So for all those I, this is perfectly fine. So now we have 3 cases to consider. Okay? Okay? S is equal to V. Then this is immediate, right? What is level I of S is same as level I minus of S. What is that? Is 0. Right? It's in any graph, this is like first vertex of the BFS, so this is 0. Okay. And if there is no path from S to V in GI, then what happens? What is the level in I of V? Infinity. Which implies level of IV is greater than equal to level I minus 1 of V. Okay? So otherwise, so we have the last case, we have a shortest UB path. Okay? We have a shortest, let S dot 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 U be the shortest, right? Shortest path from S to V in GI. Shortest unweighted path, please. Unweighted path from S to V in GI. So what is the level number here? Clearly, level of I of V is equal to level of I of U plus 1. And what our induction hypothesis implies? So look, this guy's level is whatever this plus 1. So this guy's level is strictly less than this for sure. So now I can apply induction hypothesis here. What is the meaning of that? It means nothing but level of I of U is greater than or equal to level of I minus U. That's it. Okay. So suppose we show the following. Okay. So what we will show is the following. So to complete proof, to complete the proof, I will show the following. Suppose I show the following. What do I show? I will show to you, need to show level I of U, I minus U to U is greater than or equal to level I minus 1 V minus 1. Suppose I show this to you. Then are we done? Suppose I show to you that level of I minus U is greater than or equal to level of I minus V minus 1. Then we are done, because then I can take this inequality, right? Level of I V is equal to level I U plus 1, and now I apply monotonicity here. So then I can write it level I minus U plus 1, and now this is greater than or equal to level I minus 1 V minus 1 plus 1, and that is level I minus 1 V, and we are done. Right? So if I show this claim, we will be done applying induction hypothesis and applying this inequality on this. Okay? So all is left is to show this claim. Okay. Okay, so let's try to prove that. Suppose UV is present in GI minus 1. If edge UV is present in GI minus 1, what is the meaning of this? Then clearly level of I minus 1 of V, yes, is less than or equal to level of I minus 1 minus 1, because I have edge U to V. Right? Whatever it is, whenever U comes, like in the next level V has to come. So whatever the maybe the level of U is, if I just add this, then I will get a level number of them.
It will be equality.
Yeah, it is equality actually. Yeah, it's actually equality. Okay? But in this case, are we done? Right? But in this case, we are done, right? We have proved this inequality, right? Because what is this? Level of I minus U is greater than or equal to level of I minus V minus 1. So if we are in this case, we are very happy, we are done. Okay. Okay. So now U comma V is not element of GI minus 1. What is the meaning of that? That VU is present in GI. This implies VU is present in GI minus 1. Okay? And what more? VU is present on the augmenting path. because otherwise you will not change, right? Path P. Okay, and by definition, that is the shortest path from S to T. By definition, that is shortest S to T path. Look, we are not taking any path, we are taking shortest ST path. So now what can we say? It follows that level of I minus 1 V is actually equal to level of I minus 1 U minus 1, which is definitely less than equal to level I minus 1 U plus 1. Because, I mean, plus 1, so subtract this from here, okay? And that's it, okay? So you are done. So in both cases, you have been able to show that the level of I minus U is at least level of I minus 1 comma V plus 1, and then this proof tells you this. So this is called monotonicity lemma. So what we have been able to show that if we choose different heuristics to choose this augmenting path, we might start getting good algorithm. So what algorithm I told you has a running time order m square n, and the best known algorithm runs in time order m n, but I don't think they will teach. Okay.